Hello, everybody. Mr. Settarelli here. Just wanted to give you a little more information about rational functions, the things that we've been working on with the holes and the vertical and horizontal asymptotes, and more of a conceptual understanding as to why some of these things are the way they are. So let's get started. Here we have a rational function. I've already factored it because, well, it's just easier to start talking about it if it's already factored. So our first step is going to be determining the holes. Every time we have a sort of rational function where we have some polynomial on top and polynomial in the denominator, we need to find the holes first, if there are any. And as we see, we can make a cancellation here, right? So we can cancel out x minus 2 from both the top and the bottom. And when we do that, we're left with 1 on top. This was a common mistake in class last time. It isn't 0. This doesn't magically come to the numerator. When we cancel something out and there's nothing left, like right here, there's nothing else in the numerator other than the part we cancel out, there's a 1 left over. Why? Because 1 times x minus 2 is x minus 2. So we have 1 over x plus 2. And now what do we do with the piece that we canceled out? So actually, this piece is what we're going to use to find the x coordinate of the hole. So the hole is a point. It has an x and a y coordinate. Okay, so how do we find the x coordinate? Well, we set this, the part we canceled out, equal to 0. And then we solve for x. So if we add 2 to both sides, we get x equals 2. So this is the x coordinate of our hole. How do we find the y coordinate of our hole? We plug it back into the function, but wait, is it the original function or is it the new function? We actually want to plug it into the new function. When we do that, we get y equals 1 over 2 plus 2, which is 1 over 4. So our hole is at 2 for our x, comma, 1/4 for our y. So 2 1/4. Okay, so let's return briefly back to why you plug it into here, the new function, as opposed to the original function before the cancellations are made. So for starters, if we plug in x equals 2 to this function, we get 2 minus 2 is 0 on top, and then 2 minus 2 is 0 on bottom, 0 over 0. We don't know how to deal with that. 0 over 0 is complicated. So that's like the algebra way, but I want to show you the actual like graphical conceptual way. So here I have a screenshot of this function in red. It's the function that we're dealing with. I've plotted the whole function. So I haven't done the cancellation, as you can see. We still have x minus 2 and x minus 2 in the top and bottom. And we can see this nice curve, right? We know there's going to be some asymptotes. We're not worried about that yet. Where's the hole? Well, we already found the hole. It's at 2 1/4. But that's not, we don't see a hole, right? It looks like it goes straight through, including that point. Notice on here, though, if you trace this curve, that's the function on your calculators where you can go through a curve. If you trace, you'll see that this isn't actually a point. My point for including both of these pictures here is to just kind of let you be aware that when you graph these in a graphing calculator, whether it's online or one of the handheld ones that we have in class, you will not immediately see a hole in the picture, okay? You will not immediately see a hole in the picture. Although when you trace it, you should see a hole, okay? We'll cover tracing later, I'm sure. Yes, so moving to vertical asymptotes. For the vertical asymptote, what we want to do is look at the new function that we've created after we've done our cancellations. And then we look at all the stuff at the bottom in the denominator and we set it equal to 0. So the only thing we have in the denominator here is x plus 2. So x plus 2, we're going to set it equal to 0. All right, and then we solve again for x. We can do that by subtracting 2 for both sides. We get x on the left and negative 2 on the right. This is the equation for our vertical asymptote. BA. Okay. Really, really, really important here. And I saw a lot of people were leaving this off, and it's a seemingly unimportant thing. We need to see x equals here. We can't just say -2 is our vertical asymptote. -2 is just a number. We need a line, right? X equals -2 is going to give us a vertical line, right? X equals lines are always vertical. Okay, so we do need x equals -2. And why conceptually do we have a vertical asymptote? Let's return to the graph of our original function. We can see on the line x equals -2, that's this thing I'm tracing right here, right? On this line, we can see that the function kind of splits. It goes off to -infinity in the lower part. It goes off to infinity in the upper part. If you were to pick points around x equals -2, say we started with this point here, that'd be -1.5. We can see that it's about here, right? And then if we pick a closer point, maybe halfway between these two, we're a little bit more like here. And then we get an even closer point, right? So you can see that it's just going off to infinity. Similar for down here, except it's going to -infinity. So if you were to actually evaluate all these points, you would see algebraically that they would go to numbers closer and closer to infinity as well. But that's kind of why we have a vertical asymptote. All right, and then horizontal asymptotes, the last thing here that we're going to work with. Horizontal asymptotes, honestly, it requires a little bit of memorization. So let's go into it. So for horizontal asymptotes, there are a few rules. First of all, before we even do this, let's define what degree means, because we're going to be using that word a lot. So the degree of a function is the highest power. Okay, so in our example, right, here we have a power, we don't see it, but it's a power of 1, right? If we don't see a power, it's a power of 1. So the degree of the numerator here is 1. Just going to abbreviate degree of the numerator as that. It's 1. If we were to do this multiplication really quick, we do first. So x times x is x squared, outer x times 2x. X times 2 is 2x, inner -2 times x is -2x, and last -2 times 2 is -4, and then these would cancel. We're not really worried about what this says. We're worried about the largest exponent, which we see is 2. So the degree of the denominator here is 2. Okay, so degree is just look at your x's or whatever variable you have. It's the highest degree. All right, the highest power, excuse me. That's what we call the degree. So the rules for the horizontal asymptote are based on degree. So if the degree of the numerator is greater than the degree of the denominator, we do not have a horizontal asymptote. All right. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. Okay, every time, no matter what these degrees are, if the numerator's degree is less than the denominator's degree, we have a horizontal asymptote of y equals 0. And then the last case is when they're the same. So if the two degrees are the same, we take the ratio of the leading coefficients, and I'll explain that. Okay, so y equals the ratio of the leading coefficients. But what are these leading coefficients? We look at the term with the highest degree in both the numerator and the denominator. For example, in the numerator here, the highest degree term is just x. And then the leading coefficient, it's just the coefficient of that term. Okay, so in this case, we don't see anything, so it's a 1, right? So 1 would be the leading coefficient of the numerator. For the bottom, we look at the highest degree term, right? That would be x squared. What's the coefficient on x squared? It is 1 as well. So it would be 1 here for the leading coefficient of the denominator. Okay, but we're not doing that, right? Because the degrees aren't equal. So we don't want the ratio of leading coefficients, right? The degree of the numerator here is 1. The degree of the denominator is 2. So the degree of the numerator is less than the degree of the denominator. And in that case, our horizontal asymptote is y equals 0. And just like for vertical asymptotes where you need the x equals part, you absolutely need the y equals part here, okay? Otherwise, we just have a number. That doesn't tell us much. We need a line. That's where this y equals bit comes in, okay? So, and if we reference the graph here, we can see that going off to one end, right, we're not crossing 0, and going off to the other, we're not crossing 0. For horizontal asymptotes, it is possible to do something like this. So we dip below the asymptote and then come back up, but then don't cross it again. We're not going to talk so much about that right now. We can talk about that later. Another thing, and then we'll wrap it up. I just want to briefly mention something called end behavior. This is actually pretty appropriately named compared to some other things in math that are inappropriately named. End behavior is how the function behaves going off towards the ends. And in this case, we mean the x's as the ends. So for example, as x goes to infinity, so we're going towards infinity in the x direction, in other words, to the right, we can see that our function approaches 0. It doesn't get to 0, but it gets closer and closer and closer and closer to 0. Okay, so that would be the end behavior. As x approaches infinity, our function y approaches 0. End behavior on the other side, right? Because we have two ends, not just one. The end behavior of this one, right? As x goes to negative infinity, as we go further and further left, we get closer and closer to 0 as well. And this arrow here just means we approach. So as x approaches infinity, y approaches 0. As x approaches minus infinity, y approaches 0. We will talk so much more about this. So I just wanted to give you a little intro. Okay, thank you for watching. Please let me know if you have any questions in class, and I will see you then.